Okay, my name is Chris Walney. I'm on the faculty for civil engineering here. I think most of you have probably seen me in freshman engineering at some point. The project that these guys worked on this year, I want to give you a little background on how we at Lipscomb could get involved with a project over in England. And College Study Manor, which is where these guys work over the summer, is owned by the University of Evansville. There was a fairly wealthy donor that was touring England one year back in the 70s, and he saw this manor house for sale and said, wow, what a great place for a study abroad program and bought it. And gave it to the University of Evansville with the stipulation that they offered a study abroad program there that would be available for all their students. So I taught at the University of Evansville for almost 20 years before coming to Nashville. I had an opportunity to spend a semester in Arlington and pretty much fell in love with the place. And as you'll see, it's a fascinating place to visit. A colleague of mine at Evansville, Dr. Mark Valenzuela, has gone several times to Arlington as well, and he and I are pretty good friends and have maintained that friendship over the years. He called me up about 3 years ago and said, well, would you go over to Harlexton and do a geophysical investigation? We think there's an ice house buried underneath the terrace at the manor house. And I said, sure, if I can take some students from Lipscomb. And he made the arrangements, and we ended up going over. Harlexton gave us room and board for a couple of weeks, and we went over there and did our study. One of the things that we recognized right up front early last year was that we didn't know a whole lot about ground penetrating radar and other geophysical methods that we were going to be able, or need to be able to use to see down into the ground to see if there would be a structure down that buried in the area. So I hooked up with Keele, a guy named Michael Cassidy, Dr. Michael Cassidy at Keele University in the UK, which is about a 2-hour drive from Harlexton Manor. And they are one of the top geophysical universities in Europe, maybe even the entire universe as far as I know. They're very good at what they do, have a very good reputation, and they have all the equipment that we needed if we were having a difficult time finding the kit from the United States over into the UK. So we hooked up with Keele University and Michael Cassidy and ended up with a collaborative project then that involves Lipscomb University of Evansville, Harlexton College, and Harlexton Manor, and Keele University in the UK. So I'll turn it over to these guys and they can tell you about what they did over there.
I'm Daniel Jordan, I'm the project manager. This is Amanda and Michaela, my team members. I just want to start off by telling you what we're going to tell you today. We have an introduction, how we got introduced into the project, a little bit of history about the site and the manor house itself. Our early scope last spring, what we first thought we were going to do, the methods we used to gather our results and investigation work, and a little bit about what happened when our scope changed and how we calculated what failures were going on and the design requirements that we had to meet. So Harlexton Manor is located about an hour north of London. It was built around 1840 when Gregory became rich in the lace industry. And so it's about 170 years old. And you can see a couple pictures here. This is an aerial image of Harlexton. The manor house is right here. A mile long drive comes up into the house right here around. And then the French Terrace and Dutch Canal are where we did our main areas of work. So if you can just get a visual about where we were on the grounds. And these are a couple pictures of the manor house. As you can see, the driveway slopes upward, so the manor house was actually built into the side of the hill instead of on top of the hill. And then you have a side image also of the house. This is an image inside the library, an image on the back side of the house, the greenhouse, and then the front picture of the manor house. So very extraordinary, awesome place to stay at. Some of the rooms are converted into dorms now, so that's where we stay. Some of them are original architecture. Very cool places to visit. So our senior design project, we wanted to meet these requirements, work together to achieve professional and ethical issues to achieve getting through those, and that's kind of what we set out to do, to accomplish real-world tasks.
So about our scope, as Professor Wani said in the beginning, we was approached by the Tanaka about the ice house. We had to verify if there's ice or not. But we also need to investigate the drainage system because we believe that there's a clause. And the retaining wall, we believe that we found there's a crack of one wall. We have to determine the soil pressure and how to have the work. And for some facts, there was a piece of clay pie was found the French terrace garden, and there was a cracking throughout the foundation that lead us to believe that there was a flaw in the stormwater and the desired drainage system. And again, it was built about 150 years ago, so who knows? And the retaining wall, it was built about 19th century, a long time ago. So we don't have a lot of information before we go to Harrison. So we do investigation stealth study for Land Level Farm in Nashville, Tennessee. And that has same structure. As you can see, the stack of wood and the soil and the rubble, stone rubble work behind wood and the soil back here. So it's similar to Harrison, but again, you have to go there and you have to find what's wrong with the wood, how to stabilize it. And for an ice house, as you can see, there's a sinking where the blue circle is. And we believe that there's something underneath it, but we're not sure, we don't know. We just know it's sinking and has some sediment. So we go and do some investigation. And this is a location for ice house. You can see that in the French terrace. But we also know that there's another one near the house that has some entrance to somewhere, but it was blocked. So we don't know what behind that, so it's not unknown that we have to find out. And we also know about the gazebo and the retaining wall on the northwest of the wall, where it has some cracking and movement that we need to do investigation. So we communicate with Dr. Mark Valenzuela using his data. And his student has done a good job collecting topographic maps, about 10,000 files and plot it. And also any information that we can find online, either through Harrison website, any historical website, Google Maps, Google Earth, anything we can do to help us to visualize the place that we're going to do. And we also do research on geophysical methods that we're going to use, and then we'll talk more about that in the next slide.
So we were pretty unfamiliar with geophysical investigations coming into this project. And so we had to go through a process of researching and choosing which one would help us gather the best data. So we looked at 4 different methods: electrical resistivity, ground penetrating radar, electromagnetic, and seismic reflection. And we looked at 5 different categories. We didn't want it to be destructive to the ground. We wanted it to give us a pretty great depth to see if there was a void space, to see if initially if there were any drainage issues, where the pipes were, and also determine some soil layers. So we wanted a great depth, but we also wanted great resolution to see those soil layers or to see a void space in the images. But we also wanted to learn quickly and for it to be relatively cheap to rent. And so we came up with 2 methods: ground penetrating radar and electromagnetic, that were ultimately the top 2. And we chose ground penetrating radar because Dr. Nigel Cassidy had it available for us to use and taught us when we did our site investigation. And we also verified some moisture contents of soil layers with resistivity, but didn't really do it to detect void spaces or earth layers, soil layers.
All right, site investigation and results. So priority 1, as been stated earlier, was to determine what was causing the drainage, or what the problem was with the drainage. Well, once we got there, we learned that Halton had already replaced the drainage, so priority 1 was complete. Priority 2 is the retaining wall. So we assume that the original construction of the retaining wall was with the house. So in 1840s, this retaining wall has been there. The earliest documentation that we have of the counterworks, which is seen in the picture on the right, is World War I. We assume that these were placed to stop movement of the wall, which it did stop, but now they're actually causing more harm than good because cracking of surrounding counterforts has started occurring. So as I said, cracking is occurring at the retaining wall, so we assume that the retaining wall is moving. But Well, we have this scarp line on top of the terrace, and runs about 135 feet of the terrace. The terrace is a total of about 60 meters or 100 feet. As you can see that the slope on the far side is actually greater because there's no car park there, and then that's where the counterforts are. So the greatest movement is you're experiencing up top. On the bottom, the slope is less because there's actually a car park at the base of the wall, so it's kind of stopping the movement of the wall. Then we also have buttresses, but we can see these from the settlement of the terrace. We assume that we're not seeing them before, but with the movement of the wall, terrace has been settling, so they're now seen, which was actually helpful because we were able to figure out the dimensions of the buttresses. All right, so we also have the Dutch Canal. This is located about 50 feet southwest and about 30 feet higher elevation. In the circle in the bottom is where an outlet was previously plugged. This was plugged because it was actually contributing to wetness conditions at the base of the tower, which is experiencing rotational failure, which we'll talk about a little bit later as well. So at this quarter, you can actually see on top of the ground, it's cracking. But as you go farther, it gets wetter, and we know that from electrical resistivity. Then on the far left of the picture is another outlet. The flow actually was flowing towards the base of the tower as well, but was diverted because they don't want the tower has started to fail as well. So here's the gazebo is experiencing rotational failure from, we assume, at the wetness of the tower conditions at the bottom of the soil. So Carlson actually had this previously monitored, and we know that the cracks open and close due to the shrinking and swelling of the soil. And we know this because of the Dutch Canal as well.
So this is our ground penetrating radar method that we're using. You can see Michaela is spreading out a tape measure there. It's about 30-meter line that we did. And depending on the frequency is how many pulses you have to send down per 30 meters. So for the 100 megahertz frequency, this gave us a great depth resolution down into the terrace, but didn't give us it gave us a great depth but not great resolution image. The 450 megahertz frequency, the higher frequency, gave us a great resolution image but did not go very far down. And so this is the 100 megahertz that we're using here, and this is the transmitter. You haul it along the ground surface, and the receiver receives the pulse that's transmitted into the ground, and it gives you an image right there on the screen that you can see of soil layers. It resonates through the soil. You can see a possible void space if there was one. We also pulled it along behind the wall over the buttresses. The ground penetrating radar resonates differently through stone or through air than it does soil. So that's why we chose it to use to try to detect void space and to try to see the soil layers if there was movement behind the wall. We used it actually on the wall as well to try to get the cross section, to try to see if there was what was behind the wall or how far the wall went down. And so here actually is a cross section of the wall. There's actually a little piece missing. And you can actually look down through the wall. And so in front of this brick is the outer face. Then there's a brick layer, a void space, and a stone rubble wall. Now the void space is still intact because of ties that tie between the brick layer and the stone rubble wall. And here you can see the front face of the stone rubble wall. And here's just a cross section. It's about a meter thick total, about 3.2 feet. We got the outer face, brick, void space, and rubble wall. We also used it on the car park. This car park was placed in the 1950s. It was leftover material they used after building an interstate. And so originally this did not have any gravel in front of it. It's about a 4 foot thick of gravel that they placed in there. And so we wanted to, we knew, okay, the wall is a little deeper than what it appears to be. So we want to see if we can see actually how far down it goes. And so we ran the ground penetrating radar along the base, right next to the counterforts to see if we could see the depth of those, but we were unable to find that because the gravel kind of scattered the signal the ground penetrating radar was sending.
So we also did electroresistivity. This was not one of our top geophysical methods, but Dr. Cassidy recommended it because to determine the soil moisture content at the base of the tower and on the terrace. So as you see in the bottom picture, we have 4 steel probes, and they're spaced about The greatest distance is 10 feet. As farther you get out, the farther the brick base gets sit down to the soil, determining the moisture content. We did a total of 6 lines, 2 at the Dutch Canal, 2 on the terrace, and 2 at the base of the tower. This is where we figure out that the Dutch Canal may be leaking because of where we did it and how far we went down. Even though it was dry on top of the ground, it was still wet at the bottom. So we figured that the clay liner of the Dutch Canal may be dry. And this is also kind of how we figure out the moisture content at the base of the tower as well. So along with that, we also talked to Ms. Linda Lowe, the librarian at Carliston, and she told us some about the place, and we're actually able to get into the archives in the library. And this is how we figured out when the counterforts were placed and when the scarp was present, because we have documentation of that. This is actual aerial shot. In the yellow circle, you can see 2 white dots. Those are actually the counterforts, and this dates back to when the Royal Air Force was stationed at Carliston during World War I. And then we also did some boring examples. This is how we figured out the difference between the backfill and the natural fill in the terrace. And we also did some boring examples at the bottom of the tower as well to determine the moisture content. And then here, the location of the boring samples. We did 3 on the top of the terrace, 2 at the base of the terrace. And you can see 1 and 3 are actually farther back. This is how we know that that's natural fill. And 2 is at the front of the retaining wall, and that's how we know that it's backfill. And so priority 3 was investigating the ice house. We had 2 possible locations. The first one being the arch at the front of the retaining wall, the second one leading along the house. We figured that the people of the house didn't want to see the workers. They wanted their view to be unobstructed of their land. So the workers would take secret passageways. But both of these places lead to nowhere. So we figured plans change. So we do know that there is no existence of the ice house on the property.
So, after going and doing some investigation, we realized that the drainage was complete. We verified that the ice house was not on the terrace anywhere, but we still needed to do some stabilization methods for the retaining wall. So this was our new scope of our project. So a little bit about our data we collected from Carliston. First is a hydrometer analysis of our soils, about 35 to 55% clays and the rest silts in each of the boring samples. We have engineering properties of the soils, plasticity index, liquid limit, moisture content, activity, and we were able to classify them as very thick plastic clays.
So our ground penetrating radar data, we ran about 53 lines total on top of the terrace and on the base of the terrace and then outside the ground part. And where line 23 is and kind of in the area where 5 and 6, this is a majority of the lines were ran. This is where we thought the ice house was located, but it's not. So for the ice house existence, ice house location, there should be multiple hyperbolas in between 6 and 12. As you can see, there's not. So we know that there is no ice house because the frequency would be resonating through, saying that there's a void space, but that's not there. Also, we did another run for a different frequency between 12 and 23. The same thing should be present, but it's not there, so we also know that the ice house is not. So the makeup of the wall, we ran along the wall, and we were able to, this is how we were able to determine kind of the length of the different sections. We know that the navy blue is where the facade is, then yellow is where the brick layer, the blue is the stone, no, the airspace, and then the orange is where the stone rubble wall was. So the scarp. The scarp is actually located at 10 meters, and as you can see, there's a line. It goes from about 10 to 11, and then it drops down and continues on. That's where the scarp is located. We know that that agrees with what we thought of a slope stability failure because of that separation where 10 is located. And then the buttress dimensions, we know kind of how far they go back by seeing that on top of the terrace, but what we did not know is the depth. If you look at 6 to 7, you can see how far they go back, and then you see multiple lines going down, and then it just kind of disappears. Well, that's because the GPR was not able to reach that depth, so we know that it was greater than at least 3 meters.
So, as Dan and Michaela do the GPR and macro electrical resistivity, I didn't talk about the exam, so my job is to do the 3 modeling on the retaining wall. And first we have to collect and surveying data and plotting the topographic map this has been done before we go to Harrison, because we thought that it was, we had to investigate the drainage system. And then after the trip to Harrison, we analyzed the geophysical data, the GPR data, and use that all to build the 3D modeling of the retaining wall. That's going to help us later in terms of calculation of earth pressure and maybe the geoslope, the lift slope error. And this is a cross section of the retaining wall. As you see, there's a lot of different layers behind the wall that we had to investigate. And this is a front view of the retaining wall, and this is the plan view of the retaining wall. As you see, there's two different batches, the front and the back, and we don't know how they react all together under earth pressure. So in order to understand how the wall reacts, we have to investigate all different types of mechanisms that they react or they will behave under earth pressure.
So we started determining our type of failure that we had. We looked at 3 different mechanisms: shallow failure, which is overturning and sliding to the base; deep failure, which is an overall global stability failure, which is going to move the soil layer underneath the wall as well; and then rotational failure at the tower. Now the rotational failure at the tower was 3-dimensional and kind of beyond what we could do. So that we kind of are leaving that up to structural analysis that Carlson has also budgeted for. And so our investigations were strictly geophysical, geotechnical, and so we looked at the slope stability failures behind the wall, mainly these 2. So we had Mike Marassa from Hayward Baker come in, help us look at an existing site, the Tennessee State Capitol retaining wall. We visited that site to kind of help us practice on, okay, do we have all of our data? What are we missing? Do we have our facts? What are our assumptions, our observations? Making sure those are all cleared out so we can head into and hone in on what would actually be happening. So these are the 2 failures I was talking about. The shallow is actually going to occur at the base or above the wall. The deep's going to come underneath the wall. So
I investigated the earth pressure calculation, and we do 2 mechanisms: the overturning and sliding. And as you see, this is a picture of the retaining wall. We have the high wall, which is about 6 feet high, and the lower wall, and the front batches, and we have the top part. And this top at the outer post is about 4 feet thick of gravel on the ground. So we have to investigate and by calculation how the gravel affects the retaining wall. That's what we're going to do. And we do overturning and sliding, as we see. And in terms of overturning, like we have a tipping point, and if somebody pushes me in the back, I'm going to just tip over. That's overturning. And sliding, just sliding to the soil. And I calculated that, and I checked a little bit about movement of the wall under pressure. And for the input data, again, we got a lot of information from the trip to Harrison and from the engineering records such as the driveway of the soil, the adhesion of the soil to the structure, and the unique weight of stone, unique weight of the brick, and the higher thickness of the wall. All those the higher thickness was found with the GPR. But we don't know the angle of friction of the soil, the cohesion of the soil, the depth, how far it go down underneath the ground, in the gravel, and how all those relate together. So this to verify those. And as you can see, some of the data. And we have to assume some of the thickness of the layers, such like we have to assume that it's go about 6.7 feet underneath the ground from the gravel of the top up. And these 2 diagrams with the cohesion and no cohesion. And you can see with cohesion, the earth pressure was really less because of the ZFO. It was formed, and it helps the wall a little bit in terms of sustaining under the earth pressure. And we also do the front batches and batches. And you know that is the batches, the wall and the back batches. So we have to calculate how they relate together using the formula altogether. And this hardwood is about 19 feet tall, and compared to 30.1 feet of the retaining wall, it's goes 7.6 feet underneath the ground. And as the results show you that the factor of safety slightly increase when the cohesion increases. And the friction angle increase, that makes the factor of safety increase too. But at the same time, I do both with car park and with no car park. And as you can see, the numbers significantly different. One is a fail, if less than one, it means the word is failed. And with no car park, definitely it's a fail for the world. So we calculate that, and that's the data show us. And we use 10 different cases. So with the matrices, the front matrices, the high one, the lower, and under the earth pressure, massive pressure, which is caused by the car park. And Daniel is going to do the deep slope failure on phase 1 and phase 7, which means there's a lower and higher under earth pressure of the car park. And so after my calculation, I conclude that the retaining wall fails at a different mechanism, either overturning or sliding. And the retaining wall fails when the car park is not designed. As you can see, the numbers very different, right? And the deep slope stability needs to be checked to compare those data.
So using GeoStudio, which we learned in our foundations class this semester, I was able to look at the deep slope stability. The phi angle of 22 degrees and cohesion of 0 was back calculated starting at 30, close to what Min started his calculation. So I was kind of mirroring that image to see where I would get a factor of safety of 1, which means the wall would be failing. So here you set up a grid underneath the wall, which actually sends the slope failure underneath the wall as opposed to at the wall. And you can see this has no car park at the wall, and this is the high wall. So here's the results, given a factor of safety of 1. And the scarp layer would be about 18 feet behind the wall and 9 feet beneath the wall. This is, again, the same process, just the lower wall. And a factor of safety of 1 was reached at 22 degrees and 0 cohesion. Then inputting the car park with the same characteristics. As you know, the car park was placed in 1950, so it had been there about 100 years before the gravel was installed. So it's pretty reasonable to say that it was failing with deep slope stability until this time, because with the same conditions, your new factor of safety calculated is 1.4. And that's the high wall, and then if you look at the low wall, it's 1.5. And this scarp is actually 24 feet at the low wall, as opposed to 19 at the high wall. And you can just look at this image and put 2 and 2 together and say, this is 25 at the low, and this is 18 at the high. And so it kind of verifies what we see at the scarp on top of the terrace. Here are Min's calculations and my calculations side by side. Like I said, from our data we can see that the wall was failing under deep slope stability before the car park was placed. You get a factor of 1 with no car park, or a factor of safety of 1 with no car park. Then, as the car park was placed, the counterforts were placed. You have sliding and overturning. They're also going to contribute to the failure. So all 3 failures are present during the whole construction of the wall, because they placed in counterforts, they put the car park in, which kind of stabilized it as far as a deep failure, but didn't hit so much of a sliding and overturning.
All right, stabilization method. So after our calculation, we figured we'll go with how to stabilize the wall with using a deep slope failure. But we did have some constraints. Ours wanted no additions to the wall. They didn't want it destructive, and they wanted it cost effective. Also, we had to consider ranking them with methods for cost and aesthetics. So aesthetics rank from 1 to 5, 5 being the most visually pleasing, and then cost rank from 1 to 5, with 5 being the most expensive. Least expensive, sorry. And so we had 7 methods we looked at. We immediately eliminated soil minerals, micropile slide stability, Anchor brought slope stability, and I think I thought we eliminated those three because they ranked the least out of all of them. So taking into the consideration the other four left were these, and they ranked the highest sheet pile wall, seeking wall with dry soil mixing, and anchor tiebacks. Those ranked the highest, and then we went in to see would these be feasible for us. So sheet pile wall, if you look at the presentation to the right, this is a sheet pile wall being pushed in. So something that we had to consider was the force required to push it in. The wall is already unstable, so adding additional force would the wall fail. These would be placed right behind the wall. It would be permanent, not temporary. This is also something we need to consider. And what material would it be made of? The clay has a high moisture content, so would corrosion be a factor in placing of steel sheet panels? The next would be single pile wall with dry soil mixing. So dry soil mixing, that also needs to be considered because a large force is used to mix the soil with the lime being added to create the second barrier to stop future movement. So for sheet pile wall, a depth was calculated of 37 feet. 25 feet is the lowest or the greatest distance at which the failure surface extends into the soil. An extra 12 feet is needed to resist any more movement of the wall. And then our last one was anchor / tiebacks. These would be placed either through the facade or through the stone rubble. One of the consequences we needed to consider was we didn't know where the ties was through the void space. So that would it could possibly cost fair the wall if we were to move one of those. But Harleston has already budgeted a lot of money for removing of the facade, so it wouldn't be an extra cost for them if they've already budgeted for that. And so the anchor tiebacks were calculated in the distance that needed to be placed there to be inserted into the rubble wall at an angle of about 30 degrees. They would extend 11 feet to the failure surface, then an extra 4 feet into the soil unbonded. Then the 6.5 is where they would be grouted to resist any farther movement of the wall. And the last would be the monitors. So inclinators and survey monitors were considered. We do not know exactly where the failure surface is. This has all been assumed for our GeoStudio calculation. So we do recommend that Harleston place inclinators into the ground, and any movement that occurs, the inclinometer, you can get that from the readings. Also, any movement with, or any elevation difference that occurred, the survey record would tell that. But the only consequence was the wall could fall any day. It's been moving for 170 years. It could fall tomorrow. It could fall in another 170 years. We don't know. So this is what the inclinators look like. They would just be placed to a minimum depth of what we calculated at 25 feet, extending farther just to ensure that they calculate exactly where the failure surface is.
So a little bit about our project timeline. We started in January. We got our scope, our original scope in February with a conference call with Dr. Mark. We presented our proposal to the Lipscomb faculty here in April. And then in the summer, we were able to practice ground penetrating radar at Glen Levin and do some topographic map data, or Min was able to create a topographic map. We were able to travel to Harleston in July and August. We figured out our scope was different than what we originally thought. And so this fall was spent rendering the data we collected, our soil analysis, ground penetrating radar, electrical resistivity, and modeling the retaining wall. Our preliminary findings report was sent in October to Harleston with all of that data, and a final design report will be sent at the end of this month with stabilization methods and failure mechanisms. We estimated about 1,300 working hours and only came up with about 570. This is due to Min not traveling to England with us. Not as much practice on geophysical equipment that we expected, and change in scope. We were just looking at the retaining wall when we came back from Harleston, and so we did not have to do as much as we had originally thought. So very under budget, which is good for our client. The deliverables, like I said, we already sent a preliminary findings report to Harleston. They were very pleased with the data we gathered, and final design recommendations will be sent at the end of this month. why do we do all of this? The English Heritage Foundation gives money to historic sites in England for restoration purposes. This is a 170-year-old manor house, and there is a lot of fixes that need to be made. They already have a donor that's willing to match the grant proposal they're sending to the English Heritage Foundation. They just need some more evidence so they can assure that they're going to get money from the English Heritage Foundation. So we're giving them that evidence and stabilization methods, cost-effective solutions to do that. Now they have about a 5-year project timeline, so we recommend that they put in those inclinometers. Those are relatively cheap to a stabilization cost. So to go ahead and put those in, determine exactly where the failure is happening so that you can better budget for another stabilization. Does anybody have any questions?
Why couldn't he go?
That's a long story. But I mean, the main problem is the visa that I have to apply and then they reject because I have to go back to Vietnam after going to England. So I feel like a lot of trouble. So, and again, if I stay here, I can do some calculation and some office work, but nobody wants to do it.
Did you come up with the specific cost per solution that you guys have found?
We did not.
Okay.
They have a team of engineers already kind of, I guess, they'll hire engineers to do that, so we're kind of giving them that first step, that initial recommendation.
So far, they've budgeted, I want to say they've budgeted about $500,000 for any structural fixes. But they haven't actually looked at geophysical, so they may decide they don't want to look at geophysical, just structural, or just kind of recommending them. But, I mean, it would be just extra cost on top of what is already assigned to fix what they are doing.
Definitely need to look at the geophysical, because if they just fix the structural aspects, you're still going to have the pressure from the earthwork coming in to the wall.
Yeah, I think we do suggest to go ahead and monitor the backfield of the work because from monitoring we know what's really going on. And all the calculation, all the modeling, we just have to figure what may be wrong. It's not a conclusion of what's going on.
Well, we have a couple people we want to thank, and these are our references from all of our data we collected and equations we used. Mike Rouse from Hayward Baker was a tremendous help to us. Chris Gwaltney, our faculty advisor, taught us a whole lot. Mark Herman from Geoservices came in the spring, kind of told us about geophysical methods. And Dr. Mark Valenzuela for kind of assigning us to this project and letting us go over there and teaming up with us. And then, of course, Dr. Cassidy, who was our man on the ground in England to teach us the ground penetrating radar, did an excellent job. It was really a joy to work with and find out, funny, quirky things about the English culture. So it was great to work with him.
So is there any work that could be done over there by other students?
There is. Oh. There is other work. We highly suggest monitoring the process, but we don't know. We only were able to get so much subsurface conditions analysis. We only had a 1 meter boring sample. So we highly suggest going back and take extra boring samples at a greater depth to determine kind of what more is happening beneath surface. That makes sense.
Dr. Cassidy already suggested he would like to go over there and take some students. He was about, 2 hours from Harleston, his university. They're getting new LiDAR equipment, which basically, if you can scan the whole wall, find every nook and cranny and crack, and be able to model that and exactly what's going on. And so he has that equipment available now to him, and he wants to return to use that for further projects.